In this lecture, we will learn about fracture and creep. Fracture and creep are the two distinct mechanical properties of a material which define how the material behaves in certain environment. So, like fracture is the fragmentation of material into two or more pieces, whereas creep is the time and temperature dependent deformation of the material. And we will learn about these two aspects of material as we go along. So, to define fracture, but before we define fracture, I would like to say what failure is. So, failure is very much different than fracture, because failure is the loss of functionality. Like if I have a cycle, I am riding a bicycle, and if just a little bit there is a deformation of the cycle tire, I will know that I can't ride the cycle anymore. That is the failure, or the failure of the function. There is no the tire is no more functional, so I cannot ride a bicycle anymore. So that is called loss of engineering functionality. It may not be fracture. Yeah, though the same tire can fragment into more than two pieces, still it is a failure, but also it is fragmented or fractured. So, we define fracture as a breakage of engineering component into two or more pieces, and in any engineering process we do not want fracture to be catastrophic. It means we want fracture to always provide some indication that it is going to fail, because if it fails while fracturing, it can be very catastrophic in nature. So, like say a material is being turned on a lathe machine, and if the material fails without any indication, that will be very catastrophic, because it can hit any nearby operating personnel. So, in that case it might be very damaging. But if the component or the material gives an indication that it starts deforming or starts bending itself or starts losing its shape, then we would get an idea that this material is going to fail, and we can take precautionary measures. We can stop the instrument or the machine, and then we can replace the component. So, that is why it is very important that we learn about fracture, how a material is going to fracture, or how it is going to break a particular engineering component. And the indication, the microstructural indication will be very much helpful in altering the microstructure, and then basically being able to tap the exact requirements from a particular component. So, in terms of manipulating the component and tailoring it for a particular engineering need will be very helpful, because now we can take care of factor of safety. We can also give the exact weight what is required for taking a particular load. So, designing of engineering component will become very helpful in terms of weight saving, economizing the overall component, while rendering the exact functionality that is expected out of that particular component. And this fracture can be through mechanical load. So, if I apply very high stresses or very high load to a component which it is not designed for, then the component can fail or it can fracture. Thermal loading, if I can thermally load a particular component, it can just basically fracture, because at higher temperature the strength of the material also starts degrading. So, depending on that, it can fail. Again, if I take that material and take it to very low temperatures, then even smaller impacts can fragment the material, because the material would have undergone ductile to brittle transition temperature. It means the component itself becomes highly brittle in nature. So, that can be the thermal aspect of it. Also, it can be related to the creep, as I said, at higher temperature greater than 0.4 times the melting point of the material, it can again lead to very lower strengths. Yield strength can be very low at higher temperature. So, it cannot sustain those high loading, and it can fragment. Fracture can also occur because of corrosion. The corrosion can start eating away the material. In case there is a pitting corrosion or very dramatic corrosion, the design strength of the component will not be its exact value, because now the material has been damaged because of corrosion, and it will not be able to take as much load as it is being designed for. So, in that case, corrosion can also induce much more damage for a catastrophic failure or fracture. Again, some biological entities can also lead to fracture. So, there are certain there is say a particular component is being placed where we have very high bacterial activity, and that can start doing certain leaching of the material, and in turn it will degrade the strength of the material, and then obviously the material for which it was designed for is no more serving its purpose. So, it can again fracture. Again, there are two articulating surfaces. One surface will start abrading against the other. So, even wear can cause sudden or dramatic fracture of one of the components or both of the components as well. So, we can see the fracture is very different from failure, because failure is a loss of functionality, it may not result to fracture. fracture is the final component, like even after failure the component can basically fragment, that is the next stage of failure. Or fracture definitely means failure, but failure does not always mean fracture, and fracture can be induced via many various input variables such as mechanical shock or thermal shock or corrosion of the material. It can be biological damage to the material, it can again be wearing of material, and there can be many other components as well. A combination of these or more can also induce the fracture. And just to show a feel of how the ductile and brittle fracture can be induced. So, why ductile and brittle fracture is why? Because if I am getting some indication, if a material fails very dramatically, catastrophically, like if I take a chalk piece and start I just shear it up, bend it, the material or the chalk piece will fracture in a brittle fashion. But if I take a aluminum wire, I start bending it, the aluminum wire will not break, it will start deforming, and I will have to do the process of bending many a times, so that it finally fractures. But in the process what I have done, the material has undergone much more deformation before it has been fractured, and that is very good for us, because now we are getting an indication that the material is going to fail, and now if the need arises, we can always replace that particular aluminum wire with some more stronger material or a newer material within certain design limits. So, that is the basic need of ductile and brittle fractured components. So, we can design them accordingly. In certain cases, we want to work with brittle materials. Why? Because of their very high strength, because of even their say optical properties or certain biological properties, we would want to play with brittle materials. So, in that case also we need to somehow impart much more toughening to it. We will see how we can do that as we go along. But in this slide, I will just tell about the difference between the ductile and the brittle fracture. So, what happens if I take a small piece of material and I start putting a tensile loading. So, I have a ductile material, I can have a moderated ductile material, and then I can also have a brittle material. So, let me say the initial cross section of all the three materials are the same. So, in a highly ductile material, what will happen? The material will start necking at certain stage, and eventually what will happen? It will fracture at a common single point. So, this is the fracture point in case of a very highly ductile material. So, we can see that the material will start deforming, at some stage it will start necking just to accommodate the deformation, and this neck will start going smaller and smaller. So, finally what will happen? We will have some area which is very weak, and this point contact will occur in a very highly ductile material. In case of moderately ductile material, what will happen? That will start creating certain voids in between. As soon as the material is being deformed, the neck is occurring, but not to that large extent. It will start creating some voids in between, which will try to basically merge together and will get something called a cup and cone type of a fracture. So, this region would have fractured because many micro cracks will now become much bigger cracks, and they will coalesce to form this sort of a fracture. So, we will see some sort of a cone and a cup type of a fracture. So, like we have a cone, so cone will appear more like this, and cup fracture will be something like this. So, we can see this is kind of a cone and this is a cup. So, we can see this type of fracture in a moderately ductile material, because in this case the necking is occurring to a very minor extent, and it is occurring because of coalescence of the cracks in between. Whereas in case of brittle material, there is no necking. So, material will fracture very flat. So, we will see that the surface is very flat, and apparently no deformation has occurred in the material. Apparently, what is also you will realize the difference between brittle and ductile fracture is that the fractured surface will be very shiny, whereas these surfaces will be very pretty dull when you see them. So, we can see in ductile fracture, it can be a point fracture, it can be cup and cone type of fracture, and the surface will appear pretty dull, whereas in case of brittle fracture, we will see that the surface is pretty shiny and highly flat in nature. Depending on that, the brittle fracture can again be transgranular or intergranular in nature. Trans means it is through the grain, intergranular means in between the grains. So, fracture can also be transgranular or intergranular. So, if we can see a material always have some grains. A polycrystalline material where you will see there are multiple number of grains out here and there. So, we can see in both the cases we can have some grainy material. So, we can see that we have certain grains out there. So, in a fracture what will happen, the crack has to propagate from one end to the other end. So, in the transgranular what is happening is it is going through the grains. So, it is the through the grains, this is in between the grains. So, we can see a crack once it is propagating, it can propagate like this from this end to this end, and eventually we have a fracture. So, the movement of crack from one end to the other end is through the grains, and at room temperature the strength of grain boundary is much more stronger than the grain. So, grain boundary is much more stronger than the grain. So, apparently if we have a nanocrystalline material, or it means if we have a material with very finer grain size. So, in this case if we have very finer grain size, then in turn what will happen, the crack has to encounter grain boundaries more number of times, and in process we will see a very enhanced strength of the material. So, in this case it was encountering grain boundary at 1 and 2 in a coarse grain material, whereas in case of fine grain material or a nano material, the crack is encountering grain boundary at 1, 2, 3, 4, 5 times. So, we can see it is much more, it is encountering grain boundary many more number of times. So, it will provide very high resistance to crack propagation. So, we can see a nanocrystalline, whereas a coarse grained material will show very easy crack propagation, whereas in nanocrystalline material we can see much more encountering of the crack path with respect to the grain boundary. So, we can see there will be very high resistance of the crack propagation in case when we have a nanocrystalline material. Similarly, for intergranular fracture also we can see if a crack is propagating, in this case of intergranular fracture the crack will initiate from one side and then it will follow. So, let me also draw one for the nanocrystalline. So, I will see that in this case we have a very fine grain structure. So, in this case we can see that we have very fine grain structure, and then grains will be very I am drawing little bit more systematic or very self following structure, but it will be very random in nature. So, in this case of coarse grain material, crack will initiate at one point, it will follow the grain boundary to finally fracture. So, this is the overall crack path in the case of coarse grain material, whereas in case of fine grain material or a nanocrystalline material, the crack will initiate at one point and it will start following the grain boundary, and it will start following the way it can follow, maybe somewhere it will finally. So, in this case we can see that the crack path is very tortuous, and it means that the crack has to change its path very dramatically. So, in a coarse grain material, as soon as the crack has initiated along a particular grain boundary, it can progress through certain distance without getting affected, without changing its direction. That is for the coarse grain material. Whereas in case of fine grain material, the grains are so fine that it has to come back to its original point, change its direction by say 180 degree. It was going down and it has to come up. So, in the process it is getting much more resistance because of the path, because if the crack is propagating from left to right, it has to go down and then come up. It is doing nothing but absorbing certain energy for maintaining its original path. So, in turn we can see that the crack path is very tortuous for a fine grain material. So, we can see that there is very high resistance for crack propagation in a fine grain material. So, we can see that whether the fracture is either transgranular or whether it is intergranular, a fine grained material will impart much more resistance to the crack propagation, or it will make the crack path very tortuous, or in turn the overall strength will be very high for a fine grained material. In one more term, the toughness also toughness of these fine grained material also will be very high, because now this fine grained material can also realign themselves and they can absorb certain shock. So, overall strain and the stress part can recombine synergistically to enhance the fracture toughness as well. So, generally fine grained material will have very high toughness in comparison to that of coarse grained materials as well. So, that is what we just saw in the micro versus nanocrystalline material. So, we can see that in a micro grain material we have much bigger grains, whereas in nanocrystalline material we have very fine grains. So, that part we already observed, that in a case of nanocrystalline material, the crack has to take a very tortuous path. So, in turn it can provide very high resistance to the crack path. So, in this case the crack path is much easier, because in this case it has to go here, change its direction, come back and maybe change its direction and get a very tortuous path. Also, the strength of the material also enhances as we go with lower and lower grain size. This is given by Hall patch relationship. So, we have a coarse grain, we have fine grained material. So, what eventually we are seeing, that in a coarse grained material the crack path is very easy, it can follow through very easily, whereas in fine grained material the resistance offered by the structure itself is very high, and also the strength of the material for deformation also requires even enhanced strength because of its lower grain size. So, that part is being true for the nanocrystalline material, that we can enhance the strength of the material via reducing the grain size, but that is true until only say around 20 nanometer of grain size, and below that inverse Hall patch relationship also comes into picture. That means that for grain size is lesser than say around 10 or 15 nanometer, the strength also starts degrading. So, that is the overall deal with the micro and nanocrystalline materials, and eventually what happens is that the impact and fracture also is dictated by the grain size of the material. Like I said earlier, the tortuosity has been increased, so also the strength of the material has been increased. At the same time, the nanocrystalline grain, they can also realign themselves. So, now they can absorb much more shock, and then they can impart very high impact energies, or they can have very high fracture toughness. The impact energy is nothing but it is defined as a fracturing a standard test piece. So, energy which is being absorbed in while fracturing a standard test piece. So, like we do at tensile test, this is a much more rapid form of the impact of that particular test, that we can achieve fracture very quickly. So, instead of doing the entire tensile test of loading the material and then seeing the fracture, this test can immediately fracture it. So, we can get something called a fracture toughness of the material. Impact energy, it can be identified using ISO testing, notch bar testing, or Charpy testing. In this case, what is happening is we take a notch, we develop a notch in the material, and that material is now supported on these two ends, and a impact is provided on the other side, and then this material entirely fractures. And that is thing is that particular sample is now also been tested using Charpy via using this instrumentation, that we have a load on one side, then we have our sample which is sitting, and then it will again have a notch on this side. So, a notched bar specimen is on this side, which is being held on an anvil. and for a certain height, because this has certain mass, this load, it has certain mass. So what happens is this load is allowed to free flow and impact this notched bar. So with certain height, so there will be some absorption of this energy, because we have certain load and it has certain height. Once it is allowed to flow or swing from one end to the other end, there will be loss of height. So we had certain height, and finally we can also see some h dash. So there will be lowering of height because of the absorption of this energy by the notched bar. So in turn, through this particular equation, we can always find what is the overall energy which is being absorbed by the sample. So our sample is a notched bar, so this is our sample, and through that we can also see that what is happening in terms of the absorption of this energy. So we have either ISO testing or Charpy bar testing. So this is a bar, generally it is around 10.8, around 10.6 to 10.8 millimeter square sample, and we provide a notch, and then it is basically being fractured. The top center schematic shows the for the Charpy impact testing, and in this case we have a notch 45 degree V notch, which is around 2 millimeter deep, and it has a root radius of around 0.25 millimeter, and the impact direction is shown along with. Whereas the right hand schematic shows the way in which we do the impact testing for ISO testing. So both of these methods give us the fracture toughness. So this is what we can see, that the overall impact, it basically is to fracture the sample. So this sample will fracture at wherever we have notch. So this load will start fracturing, will fracture it along the notch, and then we will see some fracture surface. So this impact and fracture toughness can be measured by using ISO or Charpy testing, and we provide a notch in the sample, and a load is swung with a certain height, and then that load strikes the sample, and there will be reduction of the height because of the absorption of energy by the sample, and by changing the height of this load, we can calculate what is the impact energy that is being absorbed by the material. It can be either provided either in joules or foot pound or Newton meters. So Newton meter comes to be joules, or it can also be calculated as foot pound, and generally energy which is being provided here is around 20 joules, or 15 foot pound is basically the minimum requirement for a particular material for certain engineering applications. Now coming to the fracture toughness. So apart from impact energy, the fracture toughness also is a very critical component of a material. So as the material will be very highly tough, it will have very high value of fracture toughness, and fracture toughness is given by Kc, that is equal to Y, that is a constant for a material depending on the geometry. Sigma c is the critical stress for crack required for crack propagation. A is the crack length. So Kc equal to Y sigma under root of pi c. And generally we can see that the thin specimen, when we have a thin specimen, the fracture toughness will start depending on the specimen thickness, because now the material can also deform along the third direction. So if we take a very thin material, it can start deforming along that side. So the toughness also will be very different. And if we don't allow the strain to be accumulated along thickness, so we can enhance the thickness of the material. So now in that case it will restrict any deformation along the z axis or the third axis. So by that we can also induce plane strain conditions. And what plane strain condition do? It becomes a fundamental property. So we can see that if we want to have a constant fracture toughness for a material, we need to have very high thickness of the material, or the crack notch should be much thinner than the thickness of the specimen, so that there is no deformation occurring in the third direction. And again, fracture toughness can be defined in terms of plane strain as mode 1, mode 2 or mode 3, and we can see that the mode 1 opening is more like this. So we can take a sample with certain thickness we can have. So we can have only the opening mode. So mode 1 is also called tensile mode or the opening mode. So we can see that it is just the tensile mode or opening mode. It can also be sliding mode. So, we can have this is called a sliding mode. This second mode is called sliding mode. In this, the top piece is being taken on the right hand side, and this thing is being taken on the left hand side along a notch. So, this is called a sliding mode. Third mode can be a tear mode. So, we can see that in this case what is happening is so, in this case we can see that this part is being taken away from each other. So, it is going towards inside this plane and this is going outside the plane. So, in this case it is called a tear mode. So, we can obtain the under these plane strain conditions when we have when we limit the deformation along the third axis. What we can do? We can do this fracture. We can evaluate the fracture toughness via tensile mode, sliding mode, or the tear mode. So, we can call it mode 1, mode 2 or mode 3 toughness. So, we will call them K1C, K2C or K3C for these 3 different conditions. Also, fracture toughness also though it is a fundamental property, it basically increases with increasing temperature, because now with increasing temperature the material is much more, it can deform very easily. So, it can absorb much more energy. So, it can provide a higher value of fracture toughness as we increase the temperature. Also, it will increase as we lower the strain rate, because as we increase the strain rate there is very minimal time for the material to adjust itself or to align or equilibrate with the surroundings. So, in that case as we start increasing the strain rate, the fracture toughness of the material decreases dramatically. The third case is the refined microstructure. As we talked about, once you have a nanograin material, what it can do, it can provide enhanced strength, as well it can accommodate much more strain into the material. So, in turn it can provide very high fracture toughness to the material. So, we can see that fracture toughness is a fundamental property. It will increase as we increase the temperature, or it will increase with decreasing strain rate, or it will also increase when we have a very refined microstructure. So, that is the trait of a material. So, once we have a very fine microstructure or a nanostructured material, it generally shows very high fracture toughness in comparison to that of micro or a conventional material which is a very big grain size. So, fracture toughness is also one of the very important properties of the material. Eventually, what can also happen, we can also observe a ductile to brittle transition, and that occurs, the brittle fracture generally occurs because of decreased dislocation velocity. So, now dislocations can't accommodate the stress because the rate of strain is pretty high, or it means once you reduce the temperature, the dislocation cannot move that easily. Also, the material has increased yield strength. So, in turn it cannot accommodate the yielding of the material. So, in turn we can achieve we will observe very brittle behavior of the material. Generally, for low strength or FCC or HCP material, they generally show very higher impact energies, but they do not show any change of this impact energy with temperature. So, DBTT, or it is also called ductile to brittle transition temperature, ductile to brittle transition temperature. So, we do not see that transition in case of low strength FCC or HCP metals, whereas high strength materials also do not show any variation in impact energy with temperature, but they are highly brittle. So, that is a problem with these high strength materials, whereas BCC materials they show a transition from at higher temperature they are very ductile, whereas at certain point they undergo a transition in which suddenly from ductile material they become highly brittle. So, that is a problem with BCC materials, and this concept came into existence because of during World War II, when many naval ships, while they were sitting in the sea, they broke into two pieces. So, these materials, the ferritic steel which had enough strength, at room temperature they were left into the sea, and because of the temperatures of that zone, the ship just broke into two pieces. So, that initiated the this study of what happens at this low temperature, why these ships are falling into more than two pieces as it is because of low temperature. And essentially we can see that there is no so that was the concept of ductile to brittle transition temperature, and eventually we will see that there is no explicit criteria. So, that when this transition is occurring, so that is being selected as 20 joules or 50% of fibrous fracture, or it is also 15 foot-pound of energy that can be absorbed. So, we can see when the impact energy is around 15 to 20 15 foot-pounds or 20 joules, we can call that as a ductile to brittle transition temperature, at what temperature that particular thing is being observed, or we can also relate it to 50% or 100% fibrous fracture also. So, in this case DBTT is given by the 50% fibrous fracture, but once it is being initiated we can take it down to say even 100% fibrous fracture as well. As we see here in FCC and HCP, we are not seeing any ductile to brittle transition temperature, and they generally are low strength materials, but they show very high impact energy. And high strength materials also, they are insensitive, but they are inherently very brittle. So, coming back to the microstructure of the material, when we have a nanocrystalline material, we are seeing decrease in the grain size, and that will allow much more deformation even at much lower temperatures, because now grains can realign, they also have very high strength, and in turn they can have very high toughness, or it means they can survive, or they can retain this higher impact energy of 20 joules even at much lower temperatures. So, decrease in grain size, it also lowers the transition temperature, that is very good, because now the material can operate at even lower temperatures, and that occurs because of both enhancement in the strength as well as toughness due to the lower grain size. So, this is one more functionality of the nanocrystalline materials, that they can show enhanced toughening in such conditions as well. So, we can see this phenomena of ductile to brittle transition temperature, how it differs from material to material, like in this case of low strength FCC HCP materials, it has very high impact energy. High strength materials, they again show non-dependence on the temperature of impact energy, whereas BCC materials, they undergo a transition, and to lower this transition is very much required, and that can be achieved via controlling the grain size. So, we can reduce the grain size and then we can achieve enhanced toughening. Now, coming to the another deformation criteria, which is called creep. Creep is a time dependent permanent deformation of a material, but it is under the influence of constant load or stress, which is pretty low, much lower than the yield strength, but at pretty high temperatures. Temperatures are ranging greater than 0.4 times the melting temperature of the material. So, we can see creep is a time dependent permanent deformation of a solid material under the influence of load or stress, which is much lower than the yield strength at room temperature, but it occurs at very high temperatures, which is to the order of greater than 0.4 times the melting temperature. And we can see applied stress is pretty less than yield strength at that temperature, and this basically occurs that long term exposure of a material because of high stress and temperature is main reason for the creep. So, if we keep a material at higher temperature, high enough temperature for long enough duration, and that material will undergo some change in the structure, it will deform permanently, and that is the cause for the deformation of the material, and that is not very much desirable, because it will change the shape of the component, and that might lead to sacrificing the safety of the component. So, that in that case we can see that the creep also needs to be controlled by enhancing its strength. So, we can utilize again certain design criteria, and we can avoid long term exposure of the material to high stress and temperature to avoid the creep. And again the creep rate will depend on the material, kind of material we have. So, if we have very high strength material, the creep will be delayed, the time of exposure. So, if we keep the material for long enough time, if we expose it for very long enough time, the creep deformation will be pretty much high. Temperature, again if we keep the material at very high temperature, the creep rate will be very dramatic, will be very high, and the material will deform very rapidly. Applied stress, so again it also depends on the kind of loading that is being incurred on the material. So, if we have very high applied stress, the material will undergo very high rate of creep. So, we can say the creep is dependent on many parameters such as material, its microstructure, the time of creep or time of exposure, temperature at which the creep is occurring, even the applied stress on which this loading is being provided to the material. Though creep induces deformation, it may or may not lead to material failure. The creep deformation can be very marginal, it can be very minimal. So, it might deform the material, but may not lead to eventual failure as well. That is one more criteria with respect to creep. But sometimes creep is very useful also, because if a material has undergone, it has say inculcated much stress because of certain processing, and once we heat it to high temperature for long enough duration, it can relieve those stresses, because now the yield strength of the material has been reduced. Now, it can release its stresses which might have incurred during the processing or even during the functionality or when the material is being utilized during the service. So, that again can reduce the relieve the stresses, and that can again avoid the failure of the component in that sense. So, sometimes creep can be a little bit useful, but it has to be in a controlled fashion. So, creep accommodates stress with time before eventually the material fails. Again, the concerned areas, because once we have a creep, it starts accumulating much more strain, or it can also starts accommodating stresses. So, the concerned areas which are affected by this creep are steam turbine power plants, nuclear power plants, jet engines, heat exchangers, and basically some places where we can have some temperature for prolonged exposures. And also some stress that is incurred on the material. So, like we have steam turbine power plants, nuclear power plants, jet engines, heat exchangers. So, here we are talking about certain temperature, certain duration on which that particular component is being operated, and also the stress which the component has to resist. So, in those three under those three conditions, we can see that it can always induce some deformation in the material, because that it is very favorable for very high temperature, around greater than 0.4 times the melting temperature. So, there is some stress or loading, also there is enough time for the material to correspond to that. So, in that case creep can become very critical. So, in this case we have to control the creep by designing, proper selection of the material, also calculating what is the temperature, what is the time, and what is the stress level that is acting on that particular component. So, in that case we can utilize certain design concepts of controlling the microstructure as well. By altering the microstructure, we can also control creep in certain sense, or by controlling the stress or temperature also we can control the creep. Creep has its own features. We can see that the creep can be divided into 3 stages. It can be stage 1, stage 2 and stage 3, and stage 1 is called primary or transient creep. So, we can see in first stage what is happening is we have a instantaneous, initially as we apply the loading, we have some instantaneous deformation that inculcates in the material. So, as soon as we apply the load, it will have certain strain that instantaneously develops, and as soon as the time increases, what we can see, the creep rate is now decreasing. Creep rate now starts decreasing, and in this case what is happening, the dislocation climb is occurring which is away from the obstacles, and also the strain hardening is occurring in the material that starts reducing the creep rate. So, the creep rate is given by the ratio of creep strain with respect to time. So, d epsilon by dt, that basically starts now reducing in the first stage. So, it is occurring away from the obstacles, and we can see the creep rate starts decreasing, and there is instantaneously some strain hardening also occurring in the material that provides enhanced resistance to the creep. Whereas in second case what is happening, it is called secondary or the steady state creep. In this case we can see the creep rate is almost constant, it is more like a straight line, and in this case what is happening, the recovery and the strain hardening, they sort of balance each other. In first case we had higher rate of strain hardening, but in case of second stage what is happening, the recovery and strain hardening, they balance each other, or the rate of recovery and strain hardening is very similar. So, what we can see here is the rate of dislocation climb equals that of that blocking that occurs by the obstacles, and this is nothing but the minimum creep rate, and this is the prolonged duration. This is the dominant factor which is basically been incurred in the second in the second stage, and that dictates how much is the lifetime of the material and again d epsilon by dt will depend on the material properties, exposure time, what is the temperature, what is the stress. So, by controlling the microstructure also we can obtain a very high creep resistant material, and in this creep basically grain boundaries are very harmful or deleterious. So, that is where the deformation really occurs. So, by incorporating nanocrystalline material, that will have very high creep rates. So, by increasing the grain size we can have much lower creep rates, because now grain is much more stronger than the grain boundary at very high temperatures. In third case, what happens, the necking starts, the stresses also increase, the grain boundary separation will occur on all that. So, tertiary creep is generally very rapid, and this duration is also very short. So, as soon as the tertiary stage starts, the damage to the material also enhances very dramatically, and as we can see, the creep rate now starts increasing very dramatically and leads to eventual failure or rupture, and that occurs by grain boundary separation. There will be formation of internal cavities, cracks, voids and so on. So, that has damaged the material to a very large extent. So, we can see the creep. Primary stage, we have lowering of the strain, lowering of the creep rate because of strain hardening. In second case, we have a balance between the strain hardening and the recovery, and the third stage we have very rapid enhancement of the creep rate, and eventually it leads to rupture because of the internal defect generation such as cracks, cavities and voids. And the creep rate is basically being given as d epsilon by dt, which is a function of the sigma, that is the applied stress, with respect to also the temperature. So, as soon as as temperature is high and stress is high, the creep rate also will be very high. It can also be given as k sigma power m e power minus q by kt. So, this can be a constant. So, this is a constant which is a combination of c by d raised to b. So, we can see that c is a constant which depends on the material and the creep mechanics, how the creep is really occurring. M and b are the exponents. So, we can see m and b are the exponents, m is the strain exponent, d is the grain size exponent, q is the activation energy of the creep related to the creep mechanism. So, depending on which creep mechanism is active, we will have a corresponding q or the activation energy related to that. Sigma is the applied stress. So, as we have very high stress, this exponent will dictate what is the material response to that particular stress, applied stress level. D is the grain size. So, as we have very low grain size, the overall value of this dB will be very low, and eventually the resistance will also be very low, because that is in the denominator. So, higher the value of D, lower will be the creep rate. So, we can see that for a nanocrystalline material, the grain size has to be very higher, or the grain boundary area has to be very minimum for this particular case, and K is the Boltzmann constant, T is the absolute temperature. So, in that case we can see that nanocrystalline grains do not serve as a good resistors for the enhanced creep rate. So, to restrain the creep, we always need to have a very coarse grained material. So, we can see the effect of temperature and the stress can be given as like this. So, we can define the creep strain along the y axis and time along x axis. So, we can see that when we have lower stress and temperature, our second region or the steady state creep region is very long, and also we have a particular instantaneous strain that is also much lower. But as soon as we increase the temperature and time, the region, the instantaneous stress also increases. Also, the region in which we have a stationary creep or second stage creep also is now reduced to very smaller region. So, that part we can see that the region starts decreasing as we increase the stress or the temperature. So, that is the effect of temperature and stress with respect to the creep rate. Also the damage is now to a very large extent, because now third stage has started very quickly. So, in this case third stage has not started yet. In this case it has started at this particular time, whereas in this case it has started much earlier. So, that will lead to very rapid failure of the component. So, as we have very high stress level or very high temperature, that will lead to a very eventual failure at a much rapid rate. But now sometimes the extrapolation of data also is very much required, because if we do creep, we might require years to complete the test, and that becomes impossible. So, there is a Larsen-Miller parameter which can take account of prolonged exposures or enhanced creep rate at elevated temperatures. So, once we know what is the Miller parameter for a particular material, we can also calculate what is the stress or the rupture lifetime of that material at certain temperature. So, the Larsen-Miller parameter can be calculated for certain stress values. So, we can see when the fracture is occurring. So, for a particular stress value, say if you want to have a particular stress value of say 100 MPa, we can get corresponding Larsen-Miller parameter. So, for a particular strain level or stress level, we can keep calculating the Larsen-Miller parameter for a particular temperature. Now, once we know that we have a stress of 100 MPa, it is giving to such and such Larsen-Miller parameter. Now, we know this term, and if you want to calculate what will be the rupture lifetime, say in this case we want to utilize a temperature of 1000 degree centigrade or 1273 Kelvin. So, now once we know what is the Larsen-Miller parameter, say it is the value of K, C is generally 20. So, we can always calculate what is the rupture time. So, we can see Larsen-Miller parameter in this case is K1, which equals temperature of 1273 Kelvin, C is 20 plus log of TR. K1 is known from this particular point, Larsen-Miller parameter, it is already known. So, K1 is known, everything else is known. What we can find, we can identify what is TR at 1000 degree centigrade. So, once we can do tests at higher temperature, we can always correlate them with the Larsen-Miller parameter, and from that we can also identify, say what will be the fracture time or the lifetime of this component at say now 300 degree centigrade. And if we actually go about testing this component at 300 degree centigrade, we might require at least 4 or 5 orders of magnitude higher time than the material which is filled at 1000 degree centigrade. So, now utilizing this Larsen-Miller parameter, now we can back calculate and we can find the rupture time using this Larsen-Miller parameter. So, that is the ideology of utilizing the Larsen-Miller parameter in calculating the rupture time. Also, the strength of obstacles also come into picture. Once we have the activation energy for overcoming the obstacles, the shear what is required for creating the shear for utilized for this creep. So, what we can see, the overall obstacle strength, it will be very strong from the dispersion. So, once we have nanocrystalline materials, and also there is some precipitation at nanoscale that can eventually induce very high activation energy. So, it means the creep process can be deterred or it can be slowed down to a very dramatic extent when we have nanoprecipitates. Once we have higher dislocations, forest of dislocations, or we can have very weak precipitates, that will lead to lowering of the activation energy, or we require lower lower stress for the shearing or the movement of the grain boundaries for this creep. And once we have obstacle strength pretty low, we require very lower shear strength for causing this creep. There will be very lower lattice resistance, or there will be very lower of solution hardening. So, in that case we can observe that the spacing between the precipitates or the dispersions is also very critical. So, once we have the spacing very near, it can induce very high very high resistance to the creep of the material. So, we can have obstacle strength which can be strong, weak or medium. So, we can see the obstacle strength, it can be very strong once we have dispersions order of couple of nanometers. Also, how well they are spread apart. So, if they are very nearby to each other, it means L is very less. So, the T the force shearing force required for their movement is also very high, and in turn activation energy is also dependent. So, that also will be very high, and we can get very high obstacle strength because of those precipitates or dispersions. So, this is very critical once we have nano phases which are present, or nano precipitates or nano obstacles, very hard obstacles which are present for reducing the grain boundary movement or even the grain coarsening. So, in that terms we can reduce the creep of the material. So, because we will have some creep, we have some pinning agents such as very fine dispersants of ceramics which can be there present in a very soft matrix to resist the creep deformation in the material. So, that is how we can enhance the creep resistance of the material by incorporation of very fine ceramic particles to resist the deformation due to creep. And this obstacle strength can vary depending on what sort of obstacle is resisting the creep deformation. So, in summary we can see that we have a fracture which can be either ductile or brittle, and that depends on the microstructure of the material. If we have very fine microstructure, that can induce much more strength and strain that can be accommodated into the material before it fractures. Also, we also observe that the intergranular and transgranular fracture can also occur in a brittle material, and how a nanocrystalline grain structure will assist enhanced tortuosity of the crack and enhancing the toughness thereby. And impact and fracture toughness, again we can see that because of enhanced strength and deformation in the material, we can also achieve very high fracture toughness in case of nanocrystalline material. Also, there can be 3 different modes. It can be opening mode, sliding mode, or the shearing mode for achieving this fracture toughness in a plane strain condition, and that becomes a minimum value of the fracture toughness, and that is independent of the thickness of the material, because once we have a very thin material, fracture toughness can start depending on the thickness. To avoid that, we can also induce plane strain conditions, and in that we can also see that nanocrystalline materials will have much more fracture toughness in comparison to the micro grain structured materials. Coming to creep. Creep is a time dependent permanent deformation of the material which occurs at very high temperatures greater than 0.4 times Tm, and stress levels much less than the yield strength. And then we have Larsen-Miller parameter to basically correlate the rupture time at different temperatures. So, if you want to do a test which is kind of impossible or very impractical, that can be also evaluated using Larsen-Miller parameter, and that dictates what is the role of temperature and stresses and obstacles in inducing certain creep resistance to the material. So, we can play with the microstructure, we can play with the temperature, we can play with the stress, or we can also play with the obstacles which are present in the material and the exposure time to eventually control the creep rate and design a perfect material for its resistance. So, with this I end my lecture. Thank you.